Hello everybody, thanks for being here. My name is Shanshan from Audio Research Group, Tampere University, Finland. Today we are going to introduce our paper, a curated dataset of urban scenes for audio-visual scene analysis. I'll start with a brief introduction. Human experience. Let us forget everything for a moment and just recall our experience on crossing the zebra line in the traffic area. If we see the traffic light turns green, then our brain will immediately know, okay, it's time to go. However, if we hear some car horn at the same time, then our brain will immediately alert us to stop. By telling this experience, we humans are so good at utilizing all senses in our body. We make decisions not only by what we see, but also by what we hear, even sometimes by what we smell. So to mimic our excellent brain systems in machine learning field, audio-visual analysis gains increasingly popularities. There are some existing datasets from YouTube. However, the quality is irregular due to the labels are generated by YouTube automatically or semi-automatically. Also, the annotations are prone to errors due to lack of human ratings. Hence, here we introduce our carefully designed dataset, Tau Urban Audio-Visual Scenes 2021. Our main contributions are listed as follows. First, we propose a curated dataset for audio-visual analysis. By saying curated here, we mean the materials are carefully selected and recorded, using the same recording equipment, and also multiple locations for each city, each scene are chosen. Second, we introduce audio-visual scene classification using joint modeling of audio and video content. Lastly, we propose a simple architecture for AVSC based on transfer learning. Let us get to know more about this dataset. How many scene classes are there? Altogether, there are 10 scene classes including airport, bus, metro, and etc. How big is this dataset? It contains 34 hours of video and is time synchronized audio material. Each of this audio and video clip lasts for 10 seconds long. How diverse is this dataset? This dataset is recorded in 12 large European cities, including Amsterdam, Barcelona, Helsinki, and etc. And more importantly, recordings were performed in multiple locations for each city and each scene class. There are different parks, different shopping malls. For airport, mostly there's only one airport in each city, but the locations were selected to be as far as possible to ensure the diversity of this dataset. What device I used? For recording the video material, we use GoPro Hero 5 session. And for audio, we use Soundman binaural in-ear microphone and Zoom F8 audio recorder. How is it recorded? As shown in this picture, the camera was mounted at the chest level on the strap of the backpack. There are some specific features need to be pointed out. First, it's a diverse dataset containing both audio and video recorded in public places from different European cities. By saying this, we mean that there aren't many datasets like this due to the General Data Protection Regulation Law by the European Union. Second is binaural audio recording, and also the video contains a number of objects moving across a static background. These two features are due to the person performing the recording is instructed not to move nor speak. This table shows the statistics of this dataset. For example, for an airport scene, altogether there are 978 files recorded in 29 different locations, last for 163 minutes. Let us look at some samples. This is street traffic. This is how tram sounds and looks like. as you may have noticed, we have blurred the faces of a human and also the car license plate of the car to protect the privacy of the people. We have the data. Now it's time to do some experiments on this dataset. In this paper, we propose a case study on scene classification. For scene classification, there are acoustic scene classification and there are also visual scene classification. For acoustic scene classification, given a short clip of audio, we extract the audio features from the feature extractor, and the feature go to classification layers to do the prediction, to predict whether where this acoustic scene happens. Similarly, for visual scene classification, given a frame of video, the video feature is extracted from the feature extractor, and the feature go to the classification layer to do the prediction where this visual scene happens in, like for it happened in airport or bus or metro, tram, etc. For feature extractor, in this paper we use the pre-trained model from look, listen, and learn. I'll shortly describe how they train the network, given a short clip of audio and a short one frame of the video. So for audio, it goes to audio subnetwork to do some processing, and for the video, it goes to video subnetwork, and both output will go to a fusion layer. So they call this whole part as audio-visual correspondence detector network. This detector is to detect if this audio clip corresponds to this video clip or not. We refer our readers to read to their papers if you are interested in their implementation. In this paper, we only use this pre-trained model as our feature extractor. So in our acoustic scene classification model, given 1 second of audio, we extract the audio embeddings from L3 pre-trained model, and this audio embedding go to the classification layers to predict where this acoustic scene happens. Similarly, for video scene classification, given 1 frame of video, we also extract the video embedding from L3 pre-trained model, and this video embedding go to the classification layers to do a prediction. And both of these two models classification layers consist of linear layer of 512, 128, and 64, and followed by one output layer of 10 corresponding to 10 scene classes. And after each linear layer, there are batch normalization, ReLU, and dropout. We have seen how human utilizes our audio and visual information. So in this paper, we introduce audio-visual scene classification. Given 1 second of audio and 1 frame of video, we extract the audio and the video embeddings from the pre-trained L3 model, and we concatenate these two features into a long vector, and these long features go to the classification layer to do the prediction. And here this classification layer consists of the same structure as each individual model, linear layer of 112, 128, and 64, and this output layer of 10 corresponding the 10 scene classes we are going to predict. We refer this method as early AV fusion model in our paper. This method, we ignore the benefit of each individual trained audio model and video model. So in this method, given 1 second of audio, and we also extract the audio embedding from L3 pre-trained model, but the audio features are taken from the second last layer of the audio scene classification model. Similarly, for the video set, given 1 frame, we also extract the video embedding from the L3 pre-trained model. Also, the video features are taken from the second last layer of the video scene classification. By doing this, we also mean that we froze the weight of the first few layers and only readjust the weight of the following layers of each individual model. And now we concatenate these audio features with video features into a long vector, and this feature go to the classification layers to do the prediction as before. And this classification layer consists of linear layer 128 and one output layer of 10 corresponding 10 scene classes we are going to predict. And we refer this method as proposed early AV fusion model. Here shows our experiment result. For audio only model, we achieve 75.8% of accuracy, and for video side we achieve 68.4, and we can see video classifier is slightly lower than the audio one. We analyzed the reason by using confusion matrix, and we found out that for video classifier, it sometimes get confused about the shopping mall from airport, and also sometimes get confused about the metro from the tram, and also from the bus. And when I check on these few files that gives not so good accuracy, I found out that even for me, it's difficult to differentiate the bus from the metro and the tram. In this late AV fusion, we achieve 80.8% of accuracy. Late AV fusion is achieved by combining the outputs of separately trained audio and video models over 10 classes to obtain the final decision. So we can see this late AV fusion already give better accuracy than each individual. This indicates us that by combining this audio and video information, it can achieve better accuracy. And this audio and video information, they help each other in making correct decisions. And our early AV fusion model gives 82.2% of accuracy. And the best one comes our proposed early AV fusion. It gives 84.8% of accuracy. And this bar plot shows the class-wise performance. The red bar stands for the audio scene classification model, and the yellow one stands for the visual scene classification model, and the green one stands for our proposed method, audio visual scene classification model. And we can see from here that almost for every classes, our proposed method outperforms than each individual model, and also it gives more consistent result over 10 classes. Here we conclude our presentation. We proposed a curated dataset for audio-visual analysis, and we also provided a baseline for this dataset using the pre-trained L3 model. We also show that joint learning brings significant improvement and more consistency in the performance. Thank you so much. If you are interested in our work, please read our papers and download our dataset and clone our Git repo for detailed implementation. And by the way, this dataset is publicly available and also is the part of the challenge in DCASE in this year.